Good morning, everybody. And welcome, I guess this is the second welcome to the Deep Spec Summer School 2018 edition. We are delighted to have you all here. We are super excited about the material that we have to share with you. And the next few days are going to be getting you launched on a lunar trajectory to get you started for your stellar trajectory that's going to be the next 2 weeks. The book that we're going to be covering in these 3 days is almost all of Volume 1 of the Software Foundations series. Software Foundations used to be a single book. As part of the Deep Spec project, we've been greatly expanding it. It now has actually 5 volumes. You'll see 3 volumes on the public webpage of Software Foundations, but in your secret copy of the most up-to-date version of the book in the DSSS 18 repo, you will find the other 2 volumes and better versions of volumes 1 and 2 and 3. So those are the ones you should be referring to this week. Before we dive in, I would like to get a sense of who's in the room. So let's see. How many people here are from the United States? Okay, quite a few. How many people are from Europe? Almost as many. How many people are from other parts of the world, not those two? Ah, excellent. So we have about a 30-30-30 split. That's great. How many people here have already finished their PhDs and are working as postdocs or researchers or professors? Ish. Okay, a few people aren't sure. That happens, those of you that haven't been through that process. And how many people are working on their PhDs now? Okay, and some people are not sure. That also happens. And how many people are not yet working on their PhDs, but maybe they will later on? Okay, so again, a pretty even split. Not quite so many people that are finished with PhDs, but quite an even split of undergraduates, graduate students. This is great. Now let me ask the hard question. We recommended beforehand that everybody try to finish as much of the material in the first, I think, some places it said 4, and some places it said 3 or 4 chapters of the first volume of Software Foundations. How many people feel completely confident that they have mastered and internalized all of the material in the first 4 chapters? That is basics, induction, lists, and polymorphism. Now raise your hand high if you feel confident about all of that material. Excellent. Thank you. How many people feel quite confident about the first 3 chapters? Okay, very many people. Good. I'm not going to ask about the other 2 chapters. There are probably some people that are just diving in for one reason or another. We will catch you up to speed as fast as possible. But I am going to be aiming the lectures at the people that have already done some work in the first 2 chapters, so you will need to scramble to catch up. My goal for this morning, my goal for the first lecture of this morning, we have 2 lectures this morning by me. The goal for the first lecture is to go very quickly through the first 3 chapters, all in 1 hour and a half. So I will not really be lecturing about those chapters. I will be scanning through my slides for those chapters simply to remind you what's in them and give you a chance to ask questions. When I lecture about this material in semester-long courses, I assume that the people in the class are a little bit shy and tentative, and we use some software called Poll Everywhere that's really great for, let me see if I can get this working while I'm talking. When I lecture about this material to tender pen students, I usually use a software that allows people to anonymously answer. If I ask a question, then people can give the answer on their phone, and it's all very anonymous, and only the aggregate is displayed on the screen. And that's a way of making it very interactive without putting people on the spot. here, I don't want to take the time to get all of that set up. And anyway, I trust that you are all adventurous go-getters who have gotten yourself to an exciting summer school all by yourselves. So I'm going to just expect that everyone will jump in and participate and raise your hand and ask questions if you don't, if I say something silly or something doesn't make sense or something does make sense but you have a further question. Yeah. And we will all have fun together. So that's my request to you, is participate. These lectures are much more fun if it's more than just the three people in the front row asking questions. So let's go straight in. The first chapter of Software Foundations is called Basics. It really should be called something other than Basics because, as some of you have noticed, there's a file called Basics in the coq standard library, and things often get really confused with search paths. If I had had one more day to prepare, I would have changed the name of this file to avoid that. Hopefully, everybody has gotten through that little bit of hassle for themselves. I think actually things have even changed in the way it works between coq 8.7 and coq 8.8, so I was having trouble with it just today. But like you, I hope, I figured it out, or I can tell you what to do. Okay, so here we are in the Basics chapter. And as you know, coq is a proof assistant. It's an environment for stating and proving precise claims about artifacts that we define. So the artifacts that we define are, in general, programs. They're functional programs in a little functional programming language called Galena. Not too different from most other functional programming languages, except in a few respects. So it has a much more powerful type system. In fact, it has a much, much, much more powerful type system than most functional languages. Maybe with the exception of Haskell, I'm not sure. And it has a few restrictions that make it useful in a logical setting. In particular, it has this funny restriction that all function definitions must terminate on all arguments. So there's no unbounded general recursion in coq, only terminating functions, and sometimes that gets in the way a little bit. There are various tricks that people use to get around it. But mostly, programming in coq feels like programming in the purely functional subset of OCaml or Haskell. By the way, how many people in the room are already OCaml programmers? And how many are already Haskell programmers? Wow. Okay, and how many are already programmers in some other functional language? And how many are not familiar with programming in any functional language at all? Okay, a few. So this will be your introduction. So then I should say it the other way around. All these other languages are pretty much like programming in the functional language in coq, only with tiny differences. In terms of syntax, the functional language in coq, it's called Galena, is most similar to OCaml for sociological reasons. Okay, so in coq's functional language Galena, we can define data types, and like every functional language, coq comes with a whole bunch of data types built into the language or the standard libraries. We're going to ignore that fact and build all of them up from scratch, just for fun to see how it's done. So we can define so-called inductive types that are just enumerations of a bunch of constructors. And we can define functions over those inductive types by pattern matching. We can instruct coq to compute with those functions. And here we're doing computation internally inside of coq. We can also, and this is a whole story that we're not really going to go into, at least this week very much, but coq has facilities for extracting functional programs written in Galena into other programming languages like OCaml and Haskell, from which they can be compiled with the industrial strength compilers in those languages, linked with libraries in those languages, et cetera. So you can actually write programs in Galena that do things like serve web pages. But that is not the main story, at least of the next couple of days. So for the next couple of days, we're living within coq and simply asking it to simplify expressions. And that's what this compute keyword does. The other way of talking about computations is to state theorems about them. And the keyword example is actually a synonym for the keyword theorem and the keyword lemma and the keyword fact. So we give one of those keywords, we give a name to the thing in case we want to use it later, and then we state what we think is a fact. In this case, it's a fact about equality between two computations. This is a kind of trivial computation. This one actually involves some simplification. And here is the proof of that fact as instructions to coq to do some simplification, and then notice that the two sides of an equality are the same. Okay. We can define other enumerated types like the familiar Booleans, and functions over those like negation. We can define multi-argument functions like and or. We can define notations for things that we previously defined that introduce, say, infix symbolic syntax for and or. And this makes programming in coq a little bit more, a little bit easier on the eyes, a little bit more familiar from other functional languages. When we come to exercises, I'm sure you've all, or at least most, encountered this. When we come to exercises, they are invitations to replace, to throw away the keyword admitted, which in the files that we distribute to you is there to tell coq, please keep processing even though this proof isn't finished, and allow you to fill it in and end it with QED, which means this is terminating the proof which should be finished at this point. By the way, the files that we distribute also include so-called tester files, and there isn't really any strong need for you to use them. We use them mainly in courses where we're grading homework assignments based on software foundations. We use the test files to do the grading ourselves automatically on the things that students submit. And we find it convenient to also distribute them so that the students can check their own work and just make sure that they're seeing the grade that they're going to get from us. But those tester files are not really doing anything else except making sure that all of the admitteds for the recommended exercises have been replaced by proofs plus QEDs. So we don't really need them here. Okay, we can define not only data, but we can define, excuse me, back up. We have defined data and functions. Coq, being a functional language, considers that functions are first-class citizens. That is, functions can be used as data, passed around, stored in data structures, and so on. And since coq is a statically typed functional language, those functions as data have types just like everything else. And those types look like something arrow something. So neg b has type bool arrow bool. And if you type in check neg b, it will come back with bool arrow bool. Okay, we can build up data types from previously defined data types. So here's a silly example where we define the type of red, green, and blue, primary colors, and then we define another data type of colors where a color is either black or white or a primary color. And the fact that primary is a constructor taking a color as an argument is encoded in its type, which is an arrow type from RGB to color. So each of these declarations, where we say inductive blah, 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 is defining a set. So, so here's the model. In Coq's view of the world, there are already, at the beginning of time from nothing, all of the data values that you might imagine. And you can think of them as either trees of constructors or functions, functional values. Some of those trees have types, others do not. So when we give an inductive definition, we're carving out a subset of those trees and or functions. Sorry, let's forget about the functions. We're carving out a subset of those trees and saying these are the ones that belong to this type. So you should think of the constructors and the ways of putting things together as existing before the types, and the inductive definitions as carving out a subset. So what subset does it carve out? Well, this one is easy. It carves out the subset containing those three constructors applied to no arguments, and that's it. This one is a little bit more interesting. It says the things in this type are the constructor black, the constructor white, and anything that you can get by applying the constructor primary to something that's in that set. And only those things. That's the final bit of the force of the inductive keyword, is it says, here are some trees, let's give a name to those, and let's say that the only things described by that name are the things that we just defined. The reason that that's important and worth emphasizing is that it gives rise to reasoning principles, because now you can say, if something was in that set, if something is in the set RGB, then it must be one of these three things, because those were the only possibilities I said. Okay, we define functions on these things by pattern matching. The new bit that we're introducing here is that patterns can contain variables. Here we're not using the variable on the right-hand side, but we can. And we do in the definition on the bottom. And we can also use the underscore character as a substitute for a pattern variable in the case where we weren't going to use the pattern variable anyway. Okay. You will see module declarations around the place. Coq has a rather powerful and interesting module system. It's based on the module system of OCaml, which in turn is based on the module system of standard ML. However, we're not going to make very interesting use of the module system in this 3 days, certainly. Not very interesting use in the whole rest of the summer school, and you don't really need to know anything about how to use the module system. You just need to recognize that when you see the keyword module foo, from then on until you see end foo, we're now in a sub namespace where from the outside after the end, you have to say foo dot something instead of just something. And the reason we introduce them is to avoid polluting the top level namespace for things like natural numbers, which in Coq have a little bit of magic special syntax that doesn't work if you define your own. So here we are defining our own natural numbers, but then we're going to close the playground and go back to the standard library ones, which are defined just the same, except for the tiny little bit of extra magic. The extra magic I have to apologize for because it's a little bit confusing. I would like, and I think the Coq developers have promised that in some fairly not too far in the future version of Coq, there's going to be a way to define your own magic just the same as you can in the standard library. The fact that I have to say there's anything magical about natural numbers is very confusing, especially for people coming really fresh to the whole idea of these data type declarations and so on. So the way I'll say it to you is, there is absolutely nothing special about the natural numbers that are defined in the standard library, except that when they get printed out in Arabic notation instead of SSSSSO. And conversely, you can type Arabic notation and that will get parsed into sequences of S followed by O. Okay.